Hello everyone, thank you very much, Ashish. I'm so excited to be here at Compose along so many enthusiastic and some very advanced functional programmers. So, Ashish says, I live a dual life. At day, I teach computers how to think code more deeply, and at night, I teach people how to think about code more deeply. So this is the talk I'm really excited about for last year, because this is hands down the coolest thing I learned in the year of 2018. I was just reading this paper about programming language semantics. It's like, oh, these two things look really different. Here's how they're the same. You do this. Like, wait, what was that? What? And it explains so many changes that I see people like myself already do. So this got all of one slide in my web course that I teach. And now I'll get to a chance to really explain why it's so cool. So, you are all here to learn. Learning is about mental representations. Mental representations are about abstractions. And abstractions are about equivalences. So let's look at another equivalence. The equivalence between recursion and iteration. Many moons ago, you may have been asked to write a recursive function that prints everything in a list. And you write code like so. And then someone else comes up and says, oh, I know. I have another way of doing it, another approach. And they give you the iterative version. And now you know that these are equivalent. And it's not really two ideas, but two faces of the same approach. You can turn one into the other. They have trade-offs. One is shorter, and the other is more memory efficient. You can automatically convert one to the other, get the benefits of both. And because you see this, these two ideas have fused into head into one, and programming becomes that much easier. So equivalences help you see things at a deeper level. But this is not just any random equivalence that I'm bringing up, because imagine for seconds you're asked to not print everything in a list, but print everything in a tree. This is no longer tail recursive. And you can puzzle out how you would turn this into a loop. You know it has to be possible using a stack. But it's not so cookie cutter. Well, what I'd like you to do is now forget anything you knew before about how you would make this iterative, because you don't need that. It's actually a special case of defunctionalization, which is what I'm going to be teaching you today. So we're going to actually be looking at 4 different equivalences, variants A and B. In every case, they are the same. There's a way of getting from one to the other. Perhaps you've already done with these changes yourself. But then further, we'll see that actually all 4 of these techniques are really all instances of one general transformation: defunctionalization and its inverse, refunctionalization. So I've titled this talk, The Best Refactoring You've Never Heard of. And this is where the metal meets the road. Raise your hand if before hearing about this talk, you've heard of defunctionalization. It's actually quite a number of hands. And keep your hands up. Keep your hands up if and only if you've heard of it as anything that other than a compiler's technique. Okay, so 2. It's actually 2 or 3. That's actually pretty impressive. It's a really advanced crowd. So the rest of you, it's the coolest refactoring you've never heard of. So defunctionalization is about turning functions into non-functions, into data structures. We're going to start with the simplest example of a filter. So here's a filter function. It's nothing special. It takes in a list of integers, and it filters according to some predicate and gives you a smaller list. So this is the code. You might have seen it 1,000 times before. But in the way that filters actually show up in applications, there's something missing here. This is Jira. This is its filters. When you're selecting a checkbox from there, you're not picking up a lambda and sending it over to the server. AWS, filtering for instances, filtering for Chrome extensions, you are never clicking on a lambda and then sending that. You're clicking on something else. Why? Because barring magic, you cannot send a function. And same goes for desktop apps. Here's a desktop task manager, desktop Jira. Here are a couple other things. All of these have filters that you can save in your preferences, so you only view a subset of things. In every case, you are selecting things, you're selecting checkboxes that are not lambdas. So you probably have an idea of how you implement this, but how does this correspond to the higher order filter function we had a slide ago? What we want to do is go from this filter function that takes a predicate as parameter to something that takes a filter data type as a parameter. So what is this filter data type? We're going to turn the functions into the data type by example. This is defunctionalization by example. Our first step is we gather all invocations of the filter function, and there's only a finite number of lambdas we can pass in when we're looking at the whole program. Okay? Now we create an enum with one case for each function. 3 possible functions. Now, we need a way to use them. So we go to filter, we replace all uses of that function with the data type. Now I have to change the filter definition accordingly. So the function type becomes a data structure, where before we call the function directly, now we apply a data structure. How does that apply work? We grab the code from the places where we use filter. Each case the data type corresponds to and use this function. And we put that into our apply. So this was turning all uses of this higher order function, finding all parameters all arguments are passed for this function parameter, and we turn it into a data type with those uses as the code for applying it. Now there's something a little unsatisfying about this story. So I have a less than 3 built into my filter language. What if I want less than 4? Less than 5? Do I need an infinite case data structure? And the answer is yes. If you manage to call filter infinitely many times in your source code, like an infinite line program. If you don't, then it collapses down. More likely than having infinitely many calls of case, infinitely many calls of filter, each with a different integer, you will have 1 or 2 calls with a parameter with a free variable for that other integer. So the full story of defunctionalization is that those free variables get stored into your data structure. So it's actually less than when we take that y and we stuff it in the data structure. And now the apply will get updated to use that. And moreover, these free variables can even be functions. So here is a lambda that takes in 2 other functions and gives you the and of them. So those functions are free variables, and they even have the same type as the filter itself, which means when we turn this into a data type, we get a recursive data type. So this data type is a language of filters, recursive filters. And I didn't design this data type, it just appeared by moving around the code that was already there. And thus, we get a huge language of filters with ands and ors, purely mechanically. So now we've seen enough of defunctionalization to start talking about its general trade-offs. The higher order version, the refunctionalized style or direct style, is open. What that means is, imagine that I'm using filter a few times. I wanted to call it with a different function. All I need to do is call filter again with some other lambda. So the higher order version is open. It's easy to add new variants. Whereas the defunctionalized version is closed. If I wanted to add one of these new operations, I need to go into filter.hs, to my definition of filter, add this data type, add to apply, and only then can I use a new case. But what I get from that is that it's serializable. It is possible to very trivially send this data structure over the wire to save it to disk, and in doing so, I get the checkboxes that you saw in the actual apps. Let's look at another example. In that one, you probably you could have looked at both the before and after the code and seen how they correspond, even without this talk. Let's look at an example where that's a lot harder. So we're back to printing the tree. So here's my tree data type. It's nothing special, has a left and a right. Just do an in-order traversal. So it traverses like this. And I'd like you to take a few seconds and try to think to yourself, how would you go about turning this code into the iterative version? And if that comes to you too easily, then think about, what if you wanted to add parentheses before and after these calls? Then how do you turn this into the iterative version? Take a few seconds. So the solution, of course, is to use defunctionalization. And we'll see the actual code, the iterative version, in a few slides. So we're going to use defunctionalization, but what functions are there in this to defunctionalize? This function returns. It finishes at some point. What happens when you call return? It runs some more code. It runs the rest of the program. And in this case, the rest is either to print the right half of a tree or to be done. You finish the entire tree. So when you run return, it does it like a function. From the perspective of the first print tree, returning from it runs the thing to print the node and the right half of the tree like a function. So a lot of you in the room already know about continuations, continuation path and style. That's exactly what I was just talking about. So the first step is to do CPS conversion on this code. So we're going to pass in the thing to do after the code is finished. And wherever we call print tree, we say do this thing after. We wrap that into a function. And after the whole thing is done, we've printed both halves of this tree. Then we say do the thing after the entire function. Now we have some functions to defunctionalize. So what we're going to do, we are going to defunctionalize the continuation. Let's do that. So there are two possible continuations, two functions to put in our data structure. One is this thing to print a node and the right half of a tree. But the other is that when all is said and done, we're going to finish. So let's grab these things. Oh yes, and when you print the right half of a tree, you have to remember what tree you're printing and the thing to do after you've printed this subtree. So let's rip those out, and we have our continuation data type. And it's either done or it prints a tree and then goes on. And in this case, and if you're using a language like Java, then this data type can be encoded elegantly as, okay, so you have a tree and continuation, except that your next continuation might actually be done. So it's a stowable continuation type. And okay, so what is this thing? So you have a tree, you have a value, and a next pointer. This is a linked list. Not only that, but the way we're going to use it is as a stack. we know we want to stack at the ends, so this is kind of exciting. Okay, so let's carry out the defunctionalization, rip out the code. Those two cases become my apply. Now, where before I actually did this action, instead I need to pass in a data structure representing the thing to do, null at the top level for I'm done, and here's a stack, a linked list, a continuation of the rest of the tree to print at the mid-level. So it involves something that kind of looks like a stack, but this doesn't look like it's really taking us anywhere. Like, we still have this big recursive function. However, it's getting us closer. Well, I'm just going to move some things around. Let's do some inlining. Apply is called once. Let's zip, move it over. Now this is interesting. Print tree is always the last thing called in this function, whenever it's called. This is now a tail recursive function. And that means we do the normal trick for making a tail recursive function iterative. Wrap it in a while true. Every place before where we would have done a recursive call, we just update the parameters and go on to the next run of the loop. And there's actually something interesting about our use of this continuation type, where we say k equals new cont, tree k. That is a stack push. K is only used once, so we can make this mutable. Where it says k equals k.next, that is a stack pop. And so this is exactly the iterative solution to this problem. And in fact, if we did have a more complicated recursion, say, if you wanted to do something after you print the right half of a tree, like print a close parenthesis, the iterative solution could get a lot more complicated, but you do the exact same process and you get the code for doing that. No thinking required. So let's review. We did a 4-step process to go from the recursive to the iterative version. First, we made it CPS, so these functions appeared, and then we defunctionalized those functions. So now we have these two mutually recursive functions passing around this continuation object. We inlined one to the other. Now it's tail recursive, and it became a loop. But of course, so the inlining is kind of just moving things around, then you can do your tail recursive emulation. The big insight that made this all possible, the real workhorse of this transformation, was to defunctionalize the continuation. So we've seen two pretty different uses of functionalization. Take a few moments to go into the history of this. So defunctionalization was invented as a compiler's technique by John Reynolds, a man well ahead of his time. I have a language like ML. I want to turn it into C. I need to get rid of all these higher-order functions. Let's turn them to data types. There's some compilers that do things this way, but the problem is you need to see the whole program to know what this data type should be. So if you're doing whole program optimization, you can do this, and some of them do. But most people like separate compilation, like compile one file at a time, and so most compilers don't do this. But then around 30 years later, this guy, Danby, he started writing a bunch of papers, and he found that this technique is actually also useful as a program manipulation technique, not for the compiler, but for people to turn a program that looks one way into something that looks very different, but does the same thing. So he started writing a ton of papers using this technique with his colleagues. And he also showed that going the other way, refunctionalization, was also useful. So he'd been doing it before, but in this paper on refunctionalization at work, he had some cool examples where he took these very old state machine algorithms, said this state machine, those things look a lot like defunctionalized continuations. Let me refunctionalize them. Let me turn them into direct style. And so he had these parsing algorithms, and he then turned into using these nested recursions that were really beautiful, but I probably could have never come up with this fancy nested recursion unless you derived it like this. So if you want to see umpteen more examples, usually in programming language semantics, just read any other paper by Danby since 2001. For our next few examples, we're going to be talking about turning the rest of the computation into a data structure, where the rest of the computation actually goes into the operating system and outside of your program. So if we're seeing how these continuations act in operating systems, I recommend this paper by Oleg and my friend Ken. So let's go into something that probably a lot of people in this room actually do on a day-to-day basis. An example of defunctionalization that many of you already do without realizing it. Web actions. So here's my favorite website, Hacker News. Oh, AI Habitat. That sounds kind of interesting. And I want to leave a comment, but I'm not logged in. So when Hacker News first came out, around 2007, it had this cool feature that was unheard of at that time. And that feature was this. I'm logged out. When I start typing in a comment to leave, it takes me to login page. But then when I finish logging in, it remembered what I was doing and it posts my comments. Wow. What is this magic? The way it worked back then, this is using continuations. So to illustrate, I'm going to show, imagine you're writing like a command line version of Hacker News. The code would look pretty different from what you would do from the web if you do things the normal web way. You say, all right, give me a comment. Oh, wait, you're not logged in. Let me print out, enter username and password. Then you print out the result of posting the comment. This is 5 lines of code, all direct style. But really, there are already continuations going on here. That from the perspective of request login, the rest of the action is a continuation. And so in web, when you request login, it actually sends a response across the network, a new web page. But the same idea is going on, that the rest of this action is a continuation. But when you do things a normal way, it's like, oh, go to login page. The rest of the action just gets lost. So for Hacker News, they decided to not lose the continuation. So here's the old version of Hacker News, the open source version. And by the login screen, it's actually tracking this function ID. The server knows that this is the hash of a lambda that is a continuation. This is the rest of my action that I want to do when it completes the login. And so that's how it remembers the comments I was in the middle of posting. So continuations. Before on all my slides, I've had to like nest lambdas and everything whenever we did continuations. Does that mean that Hacker News is written like this? This is callback hell. If you've done server-side JavaScript pre-ES6, then it's all too familiar to you. Well, yes and no, but even still, there's something really unsatisfying about this. So when you take that continuation and just turn it into an ID, a lambda, there are things you can't do. So what if something goes wrong? Say, oh, I was in the middle of doing continuation TQE. What does that mean? And also, what if you wanted to load balance Hacker News? So when you log in and actually send you to a different server, that other server doesn't have a map saying this hash ID is this lambda. You cannot send a function. So in order to load balance this, to make this work across machines, you need to do something else. And that something else is to repeat after me. Defunctionalize the continuation. So pause for a second. Let's think about why is doing this kind of interaction harder on the web than direct style? Well, is it really? I've already explained that the direct style is involving continuation behind the scenes. So let's take a closer look at that. So when I do a read, it sends a system call to the operating system. Really, the operating system now captures the rest of my program as continuation. It stores this continuation. Then it does its thing, and then it invokes continuation to jump back to my program. So this style of continuations is coroutines. The client server is also coroutines. I have a big interaction, which is split into parts. So go to display the page, that's like a system call. Then I invoke the continuation, jump back to the server. It's one action split across two processes. It's coroutines. So that suggests that we can use similar tricks to how the operating system is making your thing direct style to also make the web version nice code. So Hacker News was written in a continuation-based web server where you code in direct style like on the left, but it still runs across multiple web pages like on the right. And of course, when you do normal web programming, you really have done this part by hand. You've broken your action to pieces, one for each continuation, split into parts. Each of those is its own web page. And now, let's talk about defunctionalizing the, help me, continuation. Woo! When you defunctionalize continuation, it looks like this. That's kind of, well, that's still kind of familiar. So I have an ID saying which continuation. I have some parameters for the free variables of that continuation for the things it has to remember and what it needs to do next. And that looks a lot like things that web programmers do every single day. And that is, in fact, how modern Hacker News works, where it doesn't, instead of having a function ID, it now has an action name and values saying what to do next. So presumably, the modern maintainers of Hacker News have by hand defunctionalized these continuations and split everything into parts and ruins all the beautiful, beautiful code that Paul Graham used to brag about. So this is the story of why doing interactions in web is kind of nastier than on a command line, in that we by hand have to take these actions, break them into pieces, defunctionalize them, give them names and data structures. So if you're a normal web programmer and you really are trying hard to do things as cleanly as command line, then either you figure out how to automate this process, or you throw up your hands and weep and accept fate. I'm going to do one more example, which is very similar in flavor to this last one. Let's talk about blocking I/O again. So as before, you do a read, it does a system call, then the computer goes, does its thing, and then it invokes the rest of your program and resumes. So a lot of people don't like that. It's slow, things stop. So there are many styles of non-blocking I/O, and I want to talk about non-blocking I/O via notifications. So in Linux, this is done via sig.io. That means you tell the operating system, I want you to read this file and give it to me in this buffer. And then you keep going and doing your thing. And a bit later, the operating system says, stop. I finish your read, here it is, and it runs some code in your process saying you can now use this data. So I'm going to talk about this non-blocking via notifications I/O system. Now, of course, there are many ways of doing non-blocking I/O, but for pretty much all of them, you have all this extra stuff to worry about, and concurrency, and So let's talk about how really this kind of I/O notifications is just like the direct style, but where you have defunctionalized the continuation. So let's take our laser eyes back to the read. So here I'm going to split your system up to three parts: your program, the actual file.h code, and the operating system. So you tell the file to read, it does some stuff, it eventually goes to the operating system does its thing. Now it goes back to your file.h, update some states, saying, this file has read this many bytes, blah, 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 and then it goes to the rest of your program. So from the perspective of accessing the disk, all this stuff that happens afterwards is the continuation. If we take only part of this process, like the part immediately relevant to what happens when you finish reading, that is a delimited continuation. And so when we create a notification action, it's really this delimited continuation, this piece of the rest of your program related to when you finish the read, that gets stored somewhere and then invoked when the read is completed. So the notification actions are really running a delimited continuation, but not only that, it's running a delimited continuation in defunctionalized form. Yeah. So we've taken a big tour through various problems in programming and seen how one idea can unify all of them and help you see things at a deeper level. So helping programmers see things at a deeper level, write better code as a result, is what I do. I'd like to invite you all to a public workshop I'm giving tomorrow evening at Byte Academy called Stop Debugging, Using Data Structures to Write Code That Can't Fail. And I also have the next Word in My Web course coming up in a couple months. Yeah. So we looked at all these examples. And often when you're programming, you have an idea and you have so many ways to do it. Like when I want to do actions, async awaits, message passing, so many things. You can read a book about each of them, so much to learn. And it's really just too much to learn. Yeah. In physics, Feynman tells us that you cannot memorize formulas. You can't just go to the book, memorize the formula, learn to apply it. There's too many of them. Instead, you need to learn about the relationships between the formulas, derive them for yourself when they're needed. And so I want to do the same in programming, see many different APIs, many concepts, and see how there are fewer, deeper ideas behind them. So instead of seeing a bunch of approaches to a problem, I want you to see a web of a single design in various ways you can manipulate it to get exactly the outcome that you want. So these are many transformations. Each of them could be their own talk or article. But today I've taught you to remember one very important transformation, not to rule them all, but to rule a lot of them. And that is to, with me, defunctionalize the continuation.